Alright guys, welcome back to class. Sorry I can't be here today, but I wanted to look at a lesson to extend what we looked at yesterday on vector equations of lines. We're going to add to that the idea of intersections of lines. The interesting thing that we have to look at as we're talking about these vector equations of lines when we're looking at the intersection is there's really two things that we need to consider. That we'll look at both of them today. The first is, do the paths that these objects are traveling on intersect? The second thing is, do the objects actually meet each other? It's an interesting kind of concept here, but we've got to look at answering both of those questions depending on the situation we're dealing with. Now let me just remind you of our vector equation, basic vector equation. The vector r is our position at any given time, and that equals the starting position, or the position at time 0, plus time times b, which is our velocity vector. And we're considering a constant velocity. In component vector form, this equation would be our position vector, x sub naught, y sub naught, z sub naught. That stands for when time is 0, plus t times the velocity vector ABC. And then we can also break that down into parametric equations. And this, as you'll see, will help us be able to determine if the paths intersect and also whether or not the objects meet. So let's first of all, though, consider if we're talking about intersecting lines, how would we find the angle between those two lines? Here we have two lines, the angle R, the line R, which is 12, negative 15, 15, plus t times negative 2, 3, 1, and the line S, which is 3, 6, 3, plus S times 1, negative 4, 5. Notice here I'm using two different parameters. This variable that we use for time is known as the parameter, if you recall. I'm using two different ones because I don't want to ever assume that the times are the same here. The nice thing is, though, for this application, when we're talking about the angle between them, we're going to use this formula that we've used in the past, but we need to use it with the direction vectors. When we're looking for the angle between two lines, we need to consider what direction they are going. So that's why we're going to use the direction vectors. So when we do u dot v and magnitude of u and magnitude of v, we're going to be using the vector 2, 3, 1 and the vector 1, negative 4, 5. So first of all, to get u dot v, I need to do negative 2, 3, 1 dotted with 1, negative 4, 5. And what that's going to give me is negative 2 times 1 is negative 2. 3 times negative 4 is negative 12, so it's plus a negative 12. And then plus 1 times 5, which is 5. So this whole thing equals a negative 9. So that is u dot v. Okay. Then we have to find the magnitude of u. So this is the square root of 4 plus 9 plus 1. So that's the square root of 14. So that is the magnitude of u. The magnitude of v we'll find by taking the square root of 1 plus 16 plus 25. Okay, so 1 plus 16 is 17. Plus 25 is going to be 42. So we have the square root of 42. So now when we're going to calculate this, we're going to put these in our denominator. Okay, we're going to put negative 9 in the numerator. And now we simply need to take the inverse cosine of all of this. Alright, so let's bring up the calculator here. We have negative 9 divided by the square root of 14. So it's the square root of 14. And it also has to be divided by the square root of 42. So we get a negative 0.371153 and so on. And then we need to take the inverse cosine of that. And we get 111.79 degrees. Now, here's one thing that we need to consider. Anytime we're dealing with the angle between the vectors, we actually could have two options. We get 111.79, and as we draw two lines, we're always going to have either one acute and one obtuse angle, or unless if they're perpendicular, we'll have two right angles. When you're asked for the angle between two lines, you should always give the acute side. So we're actually not done here yet. We need to take 111.79 and we're going to subtract that value from 180. So there is the angle we're actually looking for. That brings us to the question. Let's say we have two lines in two dimensions. We'll start with two dimensions because unless you can see that they are parallel, which is pretty easy to see, either they're the same velocity or they are, one is a constant multiple of the other one, they're going to intersect. So what we do here is we need to set these two lines equal to each other, okay? Because if they're intersecting, then their positions will be the same, okay? So what we're going to do is we're actually going to find the parametric equations for each of these. For the first line, x is negative 2 plus 3s, and y equals 1 plus 2s. Okay? For the second equation, we have x equals 15 minus 4t, and we have y equal to 5 plus 1t. So what we need is we need them to have the same x position and the same y position. So what values of s and t will do that? We can do that by solving a system of equations. If the x's need to be the same, then negative 2 plus 3s has to equal 15 minus 4t. And also 1 plus 2s has to equal, that should be an s, has to equal 5 plus t. Okay? And you can solve this system however you choose. One way that might be easy in this case would be to multiply this whole second equation by 4 so that it will cancel out the t's with the first equation. So if we were to do that, this would be a 4t, this would be 20, this would be an 8s, and this would be a 4. Okay, notice I just multiplied the whole second equation by 4, and now I can add those two equations together and I get 2 plus 11s equals 35, which I continue to solve by subtracting 2 and I get 33. So 11s equals 33, which means that s equals 3. Okay? So now that I know s equals 3, I can go back and I can plug it in to either one of these equations. I'll do it to this one since it's a little simpler. And I get 1 plus 2 times 3 is 6 equals 5 plus t. And clearly 7 equals 5 plus t, so t has to equal 2. Okay? So the reason why I found both of these is because now we can double check to make sure that they're actually at the same point. So if I'm looking at my equations, here's again line 1 and line 2, if t is 2, then over here I have 15.5 plus 2 times negative 4, 1. So my position is going to be at 15.5 plus negative 8, 2, which puts me at the position 7, 7. Okay? If I use this line over here that uses the parameter s, s is supposed to be 3, so I have the equation negative 2, 1 plus 3 times 3, 2. So that's negative 2, 1, plus 9, 6. And negative 2 plus 9 is 7. 1 plus 6 is 7. So again, I'm at 7, 7. That kind of just confirms that I am actually at that point on both lines. Now, to follow this up, we have the question, would this object that's moving along this line with this velocity actually meet this object moving along this line at the velocity of negative 4, 1? And the answer to this question actually is no. And that is because while they are both located at 7, 7 at some point, the object with a parameter of t does that after 2 units of time. Usually we talk in terms of seconds. So after moving for 2 seconds, this object is at the location 7, 7. However, this object with the parameter s doesn't reach the point 7, 7 until 1 second later at s equals 3. So you could view both of these almost like, they're walking through a door, and this guy walked through the door first, and a second later this guy followed him. But in a three-dimensional situation, it's actually much easier for lines to not cross. And what we have here is we have, because we're in 3 dimensions, it's harder to get 2 lines to actually cross, and then on top of that, to determine if they actually meet is a question. Now, we found the angle between these two vectors, and we were kind of assuming that they actually crossed, but here we're going to actually prove whether or not they did. So for line R, first of all, I'm going to set up the equations, and I'll put R here so that we remember which one we're dealing with. Okay, so x would equal 12 minus 2t, again, x, and here's the x component, so 12 minus 2t. Y would equal a negative 15 plus 3t, and z would equal 15 plus t. Okay, 15 plus 1 times t. So that's all line R. Now line S would give us the parametric equations. X equals 3 plus s. Y has to equal 6 minus 4s. And z equals 3 plus 5s. Okay? So in order to determine, or if these lines actually cross, we need to get a system of equations. Now, we have 3 different equations that we could set up. So I'm going to actually set up my system using x and z, because since this coefficient's 1, I can get it to cancel out the t's pretty easily. So I'm going to set up my equation using the x parametric equation, so 12 minus 2t equals 3 plus s, and the z parametric equation of 15 plus t equals 3 plus 5s. Okay. And what I'm going to do here is I'm going to multiply this z equation by 2. So that's going to give me 30 plus 2t plus equals 6 plus 10s. Now, the reason why I did this, again, is I'm trying to solve a system of equations here. So I am going to add down here. I get 42. Notice the t's are canceled out. Equals 9 plus 11s. If I subtract 9 from both sides, I get 33. Equals 11s. And that means s equals 3. And that means then if I go back here, let's say I use the z again, 15 plus t equals 3 plus 5 times s, which is 3. So that's 15 plus 3 equals 15 plus t, so obviously t needs to equal 3. I now know what s and t would be. Okay, so I'm going to, if I plug in 3 for s and I plug in 3 for t, I know my x's and my z's are going to be identical. Now, I'm also going to, just to make sure that this actually works, so I need to make sure I plug it into all three. So if I do that here in R, I get 12 minus 2 times 3, so 12 minus 6 would give me 6. Negative 5 plus 3 times 3, negative 5 plus 9 would be negative 6. And then 15 plus 3 would give me 18. So that's for line R. For line S, 3 plus S was 3, so 3 plus 3 is 6. 6 minus 4 times 3, 6 minus 12 would be a negative 6. And then I have 3 plus 5 times 3. 5 times 3 is 15, plus 3 is 18. And you can see here that we actually do end up at the same point. So this is the intersection point. So the answer to the question, did these lines actually cross, is yes, they did. They did at the point 6, negative 6, 18. So then the question is, do the lines actually meet? And the cool thing is we don't have to do any more work because we've already done all the work we need. And the fact of the matter is, yes, they do actually meet because notice our parameters ended up the same. So line R ended up at this point 6, negative 6, 18 when t equaled 3. And line S also ended up at the point 6, negative 6, 18 when S equaled 3. So they were at the same place at the same time. Therefore, they did actually meet. So now that you've seen a couple of these done, I want you to take some time and try these first few problems. Page 325, 1 to 4, page 336, number 4. Okay, so you have these. Some of them have multiple steps, and that's okay. Okay, and you can stop here, even though there are more in the PDF. Those we're going to look at next time we meet after we go over these initial problems you're working on today. Okay, I hope this is helpful, and if you need help, ask a friend and work together, and you guys can figure it out, I'm sure. All right, have a great day. We'll see you on Monday.